this example, I have two currents that are carried by long straight wires. I1 is going down the page. I2 of 2 amps is going up the page. And the two wires are very long straight wires, and they're separated by a distance of 20 centimeters. We want to find the direction and magnitude of the magnetic force that these two currents are exerting on one another. The mechanism for this force is, well, current 1 is going to make a magnetic field. That magnetic field is going to push on current 2. Current 2 makes a magnetic field, and that magnetic field is going to exert a magnetic force that pushes on current 1. Right, so let's look at the magnetic fields first. So current 1 is going to make a magnetic field. So the current is going down the page. So to the left it's going in, and to the right it's coming out. So in cross section, it's cutting through one magnetic field line to give us a sense of an orientation. So always to the right of current I1, magnetic field is going to be coming out of the page. To the left of current 1, it's going to be going into the page. So in particular, at the location of current 2, wire 1 is making a magnetic field that's coming out of the page. Now let's do the same for current 2. Current 2 is going to make a magnetic field that to the left is coming out, and to the right is going into the plane of the page. So that same idea, if I cut in cross section through one of those magnetic field lines, everywhere to the left of current 2, I have a magnetic field that's coming out of the plane of the page, and everywhere to the right of current 2, I have magnetic field lines that are going into the plane of the page. And then in particular, at the location of current 1, current 2 is making a magnetic field that comes out of the plane of the page. So now let's work out the directions of magnetic forces. So the magnetic force on current 2 due to magnetic field 1, I've got current 2 going up the page, magnetic field 1 coming out of the page. So the force on 2 due to 1 is going to point to the right. So the force on 2 due to 1. And then similarly, it's going to sort of hurt my hand to do it, but the force on current 1 due to magnetic field 2 is going to point to the left. So that's the force on 1 due to 2. And we will observe to our great relief that, at least in terms of direction, so far so good, that the force on 2 due to 1 is minus the force on 1 due to 2. We'll work out the magnitudes here in a second, but so far so good. This obeys Newton's third law, as we know it must. All right, a short version of this that you might want to keep in the back of your mind. So in this case, I have currents going in opposite directions and they're repelling each other. If you go through and flip the direction of one of these currents and try this same exercise, you're going to see that those currents actually attract one another. So what we have so far, it's just a short little thing to try to remember, is that parallel currents will attract, and opposing currents, as we drew in this example, repel. All right, now let's look at the magnitude of things. the force on current 2 due to magnetic field 1 is going to be I2L times B1, and this is a long straight wire, so we know what its expression for its magnetic field is. I2L, I'll have mu naught I1 over 2 pi d. So that will be mu naught I2 I1 over 2 pi d in magnitude, and an L. All right, if we look at the magnitude of the force on 1 due to 2, so it's current 1 that the force is being exerted on. The current has a length L, and it's being acted on by magnetic field 2. So we have I1L mu naught times current 2 over 2 pi d. So that's going to be mu naught I1 I2 over 2 pi d times L. And it doesn't matter whether we multiply 2 times 5 or 5 times 2, we're going to get the same answer. And then one sort of little subtle point that's swept under the rug, this is the expression for the magnetic field from a long straight wire. In principle, it needs to be an infinitely long wire, so this question is really only sensible to get what is the force per unit length. So we can observe in the magnitude is the force on 2 due to 1 per unit length is the force on 1 due to 2 per unit length. Just divide both sides by L, so we would get something that's finite. And that's going to be mu naught I1 I2 over 2 pi d. In terms of plugging in the numbers and practicing with that, we're going to have the force per unit length. Mu naught is 4 pi times 10 to the minus 7, and that is Tesla meter per amp. I've got I1 is 5 amps, I2 is 2 amps, and we've got 0.2 meters. So give me a 10, I'm dividing by 0.2, multiplying by 5. So we'll have as an actual number, force per unit length times 10 to the minus 5, and we want to think a little bit about the units here. So a Tesla is a Newton per meter per amp, so I'm going to have a Newton per meter per amp, meter over an amp. I've got an amp squared over a meter. And that is just going to work out. Meter crosses out meter, amp squared. So it is newtons per meter as we need.